These problems on binary search should go pretty quick. There's only a few things that they can really ask about binary search, and there's only a few really important things to keep in mind. The first important thing to keep in mind for binary search are the restrictions. Let's look at this problem right here. In this one, they have a lot of extra details that we don't care. We know that they're trying to do a binary search. We know that it says it correctly implements a binary search. Now, the only restriction that matters for binary search is that when you do a binary search, the list has to be sorted. It's this right here. Now note, by the way, it doesn't have to be sorted in ascending order. It can be in descending order. It just has to be sorted. Also, it doesn't only have to be numbers. You can actually do binary search on a list that has words as long as they are in some kind of sorted order, alphabetical or reverse alphabetical. Note once again, this is the only restriction for binary search. The list has to be sorted. This is a more specific version of the previous question. Here we're actually given 3 lists, and it's asking us which of these can we actually do a binary search on. Now, if you actually look at these 3 lists, all 3 of them are sorted in alphabetical order or numerical order. Notice this first one here, for example, this one is actually sorted in alphabetical order. So even though it's words, we can still use binary search on it. Kind of like if we were on the dictionary, right? You would be able to do a binary search on a dictionary by basically splitting it in half each time. This one here is more clear. There's a lot of duplicates here, but that's just trying to trick you, right? This one's still sorted in numerical order, 5, then 6, 7, and 8. So we can use binary search on this for sure. And this one's also tricky because this one is sorted, but it's sorted in reverse order, right? It's going from high value to low value, but it is still sorted. And the only restriction for binary search is that it has to be sorted. So these are all valid. So the answer here is actually D. This question is asking about the efficiency of binary search compared to a linear search. So if you recall, a linear search is that where if you have like a list with like 1, 2, 3, 4, 5 items, you would have to search through each item individually, right? So you might search 1, 2, then 3, then 4, then 5. You'll basically have to search from left to right. Whereas binary search, you're able to start from the middle and then cut it in half each time. However, you have to be a little cautious, especially when you see words like this. Sometimes these problems will have something like in all cases. Whenever you see something like in all cases or every time, you have to be a little cautious to see whether you can find an exception. So let's take one example here. Let's say you have a list that has these items, 1, 2, 3, 4, and 5. And let's say we're using a linear search and we're looking for the value 1. That will actually complete in exactly 1 check. It'll complete right away because it's the first item. Whereas the binary search would actually start here, and then it would move to the left, and it would check 2, and then it would check 1, right? It would be breaking this in half each time. So first this, then this, etc., until it reaches 1 item. So in this case, binary search is actually slower because the item was the first item, and it's just one exception case. But it's one exception case is actually enough to say that A is not correct, because there is one case where a linear search will actually be faster. However, we can definitely say that generally the advantage of using a binary search over a linear search increases as the size of the list increases, right? That's definitely true. So binary search is most advantageous when the values get very big, but also just in general, it tends to be better than linear search, even though there are very small exceptions. Note some of these other ones here, by the way. Whenever it talks about fewer lines of code, the amount of lines of code that it takes to write something has no bearing on whether it'll be more or less efficient when you run it. Generally, more complex algorithms take more lines of code to write, but that's not always a rule. Definitely isn't always going to be a determinant like it seems to suggest here. And finally here, using linear search is preferable to using binary search if there's a chance the target may not be found in the list. It's actually the other way around. If you use a linear search, it means that you will have to search every item in the list, and a binary search will only search a small number of them. Here's a real quick problem where it asks basically whether or not this is binary search or linear search. This actually is very straightforward. We have a procedure here. It says that it's going to look for the target in the list, and if it's found, it returns true, otherwise it returns false. And we see very clearly here that this is just a very common linear search. It's just going to go through each element in the list. If it finds the element, it returns true, otherwise it returns false. This is basically just the simplest way to write a linear search. So because of this, we know that this is not binary search, it's linear search. And the advantage of it over binary is that it works whether or not the list is sorted. So the answer here is just 2. Now here's a pretty common type of problem for binary search that deals with basically the efficiency, the actual numerical efficiency of the search. And it'll usually be framed like this, right? So you'll have like a list with like 200 items, and you want to do a binary search. So what's the close estimate of how many checks you're going to have to do? The way to do these is actually pretty strategic, and you can always use this approach. What you'll do is you'll keep dividing this by 2 until you get the number 1. So if we divide this by 2, so this is one operation, divided by 2 again, you get 50, and you get 25, and then you can round down. Now we divide 25 by 2, which we get 12 and a half, but let's just round it down to 12. Then we divide that by 2, we get 6, and then 3, and then let's say we get 1. So by the time we get to 1, how many times do we have to do this? 1, 2, 3, 4, 5, 6, 7. So basically, it was about 8 operations, right? So that's the answer here. Just as basically what you want to do. Just keep dividing it by 2 until you get to the number 1. And that'll be how many checks it requires. What this basically means is if you compare this to a linear search, it only took us about 8 tries to find the number. Whereas if it has a linear search and you don't find the number, like it's not in this list, it'll actually take 200 searches, right? You have to look through all 200 items. So we're comparing here 8 to 200. It's quite a lot more efficient. So here's another one of these. This one, this time instead of 200, it has 10,000. So let's do it again with 10,000. So here we start with 10,000, divide that by 2, we get 5,000. So let's count how many this is. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 operations. Notice sometimes I round it up, sometimes I round it down. It doesn't really matter. You're basically going to get to the same solution if you round up or down for these. Maybe you'll be off by 1 in some cases, but it'll get you pretty much where the answer is. So 13 is closest to 15 here. Okay, let's do one last problem. So in this one here, this is a bit of a weird problem, but basically we have 2 lists, one with 700 elements and one with 900 elements. And basically what it says here is that we're going to be performing a binary search on list 1, but then we're also going to be doing a binary search on list 2. Now what it's asking here is roughly how different are the number of times we have to do binary search on one versus the other. So basically what it's asking is if we have 700 items or if we have 900 items, how many different number of searches do we have to do if we use a binary search? Now the options here are basically it's pretty much the same, or it's 10 less searches, or 13 less searches, or 200 less searches. Now remember in the previous problem that when we had 10,000 items, it was about 13 searches overall, right? So we know that with a much bigger number, it's still only about 13 searches, which means neither of these can really be correct. Just to be specific, let's actually look at how many searches would it require for something with like 1,000 items. So 1,000, we go 1,000 to 500, 500 to, let's say 1. So this is about 1, 2, 3, 4, 5, 6, 7, 8, 9. It takes about 9 searches overall to find something in a list with 1,000. So we know it's going to be pretty much the same for a list with 700 or with 900. It's going to be about 9, maybe 8 searches. So it's certainly not 10. It's certainly not 13. It's definitely not 200. Really, the values are pretty much the same. If you really don't want to reason through it this way, what you could actually do is you could actually just do the same math we do for these two, which is just keep dividing them by 2. And you'll find out the number is pretty much the same. It's maybe different by 1, but you don't really need to do that. And we won't do that here, but I'll leave it to you to do that exercise. Anyways, the numbers are pretty approximate. The lesson here is that binary search is very efficient on really big numbers.